We use it literally every single second of the day. But how often do we stop and think about what it actually looks like? Today's explainer is all about the futuristic, intensely physical reality of the internet. We're going to map out exactly how human connection works on a global scale.
So, where does the internet actually live? We hear terms like the cloud or going wireless all the time, right? It kind of makes the whole thing sound like this magical, invisible force field just hovering in the sky, handing out Wi-Fi. But let's go ahead and completely shatter that myth right now. The internet doesn't live in the air. It is a massive, tangible, deeply physical infrastructure. We're talking millions of miles of copper, glass, giant routers, and deep-sea cables.
Okay, let's dive into this. Here is our map for today. To track a single data packet's journey: birth of the network, leaving your device, the global interchanges, under the ocean, and finally, the speed of light. Section 1. Birth of the network, from ARPANET to the world. To really grasp the sheer scale of this physical infrastructure, we got to trace it back to its roots as a U.S. Department of Defense project. Picture this, it's 1969, and the very first successful connection happens between a computer at UCLA and another one over at the Stanford Research Institute. A student programmer tries to type the word login. Well, the system actually crashed after just 2 letters. So the first message ever sent across the web was literally just "low." From there, the idea spread like wildfire. By 1983, they installed version 4 of TCP/IP, which became the standard protocol that finally allowed all these separate networks to join together into one giant network of networks.
Section 2. Leaving your device. The first mile.
Let's zoom right in on your actual device and start the journey of sending a simple request. When you shoot off an email or jump on a video call, your data isn't just sent as one big chunk. Actually, it's broken down into what we call packets. Think of a packet exactly like a giant puzzle or one of those Russian matryoshka nesting dolls. The pure data you're trying to send, that's the innermost doll, and it gets wrapped in all these outer layers of routing information. One layer has your house number, the next is the street, then the town, the state, all the way out to the country. As your data hits borders and towns, those outer layers get peeled away until the pure data is finally handed off at its destination.
But how does a packet actually know where it's going? Well, just like the post office can't deliver a letter if the envelope just says Joe, the internet relies on IP addresses. When you type in a domain name, like a normal website URL, domain name servers, or DNS, act basically like a gigantic global phone book. They translate that web name into a locatable IP address, giving your packet a very specific numerical target to hit.
Now, what's really interesting about this is the split between your private and public identity. Your private IP is kind of like your first name inside your house. It tells your local router which device is your laptop or your phone, but it means absolutely nothing to the outside world. Your public IP, on the other hand, is your globally recognized street address. That is exactly how the entire global network knows where to send information back to you.
So let's trace the actual physical sequence here. Say you're making a video call across the country. First, your packet zips through your home Wi-Fi network. Then, it physically travels over a copper or fiber cable buried down your street, what they call the last mile, right to your internet service provider's central office. From there, it heads to a colocation facility or an internet exchange point. This is where different networks physically plug into each other, eventually handing your data off to the massive Tier 1 networks that carry it out into the wider world.
What actually happens when it hits that central office, though? Well, when all those copper lines from your entire neighborhood converge at the ISP, the equipment there detects tiny changes in electrical voltage on the lines. It takes those voltage changes and converts them into pure digital ones and zeros. This process is called demodulation. Once that's done, your data gets bundled together with everyone else's and fired as literal pulses of light down buried fiber-optic cables toward the wider city.
Section 3. The global interchanges. Routing the world.
All right, so we've officially left your neighborhood, and your data is slamming into the massive infrastructure that actually routes global traffic. At this citywide level, your data is handled by Tier 1 ISPs. These are the absolute giants that physically own the high-speed fiber optic lines spanning multiple countries. They use these humongous routers with tables containing over 500,000 entries. They match IP networks to an ISP using something called an Autonomous System Number, or ASN. And because these Tier 1 networks are so massive, they usually set up what's called settlement-free peering. Basically, they just agree to let data bounce between their networks for free, letting it navigate the globe seamlessly. And this brilliantly illustrates why we have Internet Exchange Points, or IXPs.
You can think of them exactly like national airport hubs. An airline isn't going to fly passengers overseas just to put them on a domestic connecting flight, right? They exchange them locally. ISPs do the exact same thing for data. They let networks exchange regional internet traffic right there on the spot. So if you're just connecting to a server in your own country, your data doesn't have to take some slow, expensive, unnecessary trip across an ocean.
Section 4. Under the ocean. The deep sea backbone.
But what if your data does need to cross an ocean? As our packet takes a dive into the deep sea backbone, just look at the unbelievable physical engineering happening here. On the shore, you have terminal stations managing the network and pumping power directly into the submarine cable. As those optical signals travel through the dark, deep ocean, the light actually begins to naturally fade. So engineers place deep-sea repeaters periodically along the cable. These use semiconductor laser pumps to physically blast the optical signal with more energy, pushing your data all the way across the ocean floor.
The anatomy of these cables is just absolutely fascinating. Your actual data is traveling on pulses of light, bouncing through glass or plastic fibers that are literally as thin as a single human hair. They use this crazy technique called wavelength division multiplexing to shoot multiple signals at different colors simultaneously down the same tiny thread. And as they get closer to the shore, these incredibly delicate fibers are wrapped up in some seriously tough marine shielding. That heavy armor stops them from getting completely destroyed by shipping anchors, fishing nets, and whatever else is moving around down there.
The sheer scale of this is mind-boggling. There are over 500,000 miles, specifically over 550,000 miles of fiber-optic cable currently buried under the sea worldwide. It is this massive, incredibly complex web of glass just sitting down at the bottom of our oceans, keeping the continents talking to each other.
Because of this intense infrastructure, the capacity we're dealing with is unbelievable. Take the Maria cable, for example, owned by Microsoft, Facebook, and Telsius. It crosses the Atlantic pushing 200 terabits per second. And Google's DNS cable? That one reaches an astonishing 250 terabits per second, using space division multiplexing to just pack in even more fiber pairs. To put that into perspective for you, that is roughly 16 million times faster than your average home internet connection. Literally, no contest.
Section 5. The speed of light, latency, and the return. All right, our packet has finally crossed the ocean and made landfall. It arrives at a massive data center. Here, the signal might actually transition from those light pulses back into electrical signals on copper wiring. It navigates the local maze of the data center until it finds the exact physical server box that holds the website or the video you asked for. That server processes your request and instantly sends the data streaming all the way back through that exact same physical journey.
So the crucial point here is a concept called latency. Think about this. Despite traveling from your laptop to a central office, across the country, under the freezing ocean, into a server, and all the way back, this entire global round trip typically happens in less than 500 milliseconds. That is less than half a single second for a beam of light to circle the globe, grab your data, and deliver it right to your screen. And you know what makes this whole system incredibly resilient? Redundancy. This is the true power of the web. If a cargo ship drops an anchor and accidentally snips an undersea cable, or if a massive router just dies in a city, the internet is fundamentally designed to instantly find an alternate road for your data. The routers are constantly updating each other, so the traffic just effortlessly routes around the damage without you even noticing a hiccup.
We finally reached the end of our map, so the next time you pick up your phone or open your laptop, I want you to look at your device not as some magical wireless box pulling things out of thin air. Look at it as the very tip of a multi-million-mile physical wire. You are literally physically tethered through glass, copper, and light to the rest of humanity. It is an absolute engineering marvel right at your fingertips. You are connected to the entire planet. So, are you ready to explore it?